Welcome to the video lecture series of solid-state devices. Course code is E301. This lecture from the chapter of Junction Field Effect Transistor. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology. This is Module 4, Field Effect Transistor, Lecture 6. So, junction field effect transistor. This is the construction, field control action and characteristics, pinch of voltage derivation and numerical problem. This lesson plan is particularly on numerical problem. This is lecture 11. Henry Petrosky, one of the famous scientists, told that engineering is achieving function while avoiding failure. And for this, we have to do circuit analysis. So this lecture is particularly, we will find some solution of numerical problem. We will analyze the circuits to make avoiding failure in our future. This is the data sheet of JFET. We will see it later on. Construction of N-channel JFET and schematic symbol. Now it is known to everybody. The bulk material is N-type silicon. This is P+, heavily doped P region. This gate, drain and source region. Circuit that can be used to measure N-channel JFET characteristics. Actually, this gate to source voltage, this gate to source region are reverse biased. This VGS is reverse biased. See, this side, this is connected to the negative terminal of the battery gate and source is connected to the positive terminal of the battery. And drain source is forward bias, VD is plus, VS is minus. This VDD is positive, connected to drain terminal, negative terminal connected to source terminal. One voltmeter is connected. Here is another voltmeter to measure the gate to source voltage, and this is to measure drain to source voltage. This is ammeter to measure the drain current connected in series. So this is actually N-channel JFET switch. Here we can see that when the device is off, it is open. When the device is on, it is closed. So when it is on, the FET is off when input voltage Vi is less than VGS off. And when Vi equals to 0 or above, then the FET is on. So here we can see the cascade connection of FET, because we have to understand how the circuit is made. The output of one amplifier is the input to the next amplifier. So the overall gain AV equals to AV1 into AV2. If AV1 is the gain of the first amplifier and AV2 is the gain of the second amplifier. Note that DC bias circuits are isolated from each other by the coupling capacitor, and the DC calculations are independent of the cascading. So here we can see the FET cascade amplifier. Here we can see this is Q1 FET1, Q2 FET2. This is connected through this coupling amplifier, coupling capacitor, VDD is connected. So what will be the gain? The gain will be AV equals to AV1 into AV2. The gain of this first stage is AV1 and gain of this second stage FET is AV2. So the overall gain is the multiplication of both these two. And the input impedance is RG1 and the output impedance here equals to RS2. So moving to the next slide, this is the Darlington connection. Darlington means this type of connection is called Darlington connection. That means this is an example of using BJT. FET can also be connected in this way. Collector shorted and one emitter is connected to the another base. Now, if we go through the numerical problems of JFET for the better understanding of the FET characteristics, we can see that DC load line is there. So what is DC load line? So the DC load line for a JFET can be easily drawn by remembering the following 2 points. That is, at ID equals to 0, then VDS equals to VDD. This x-axis for VDS, y-axis for ID, drain current. Here we can see that VDS equals to VDD when ID equals to 0. And when VDS equals to 0, then ID equals to VDD by RL, this point. So if we connect these 2 points, we will find the DC load line. This is a straight line. The Q point is generally situated at the middle point of the load line for class A operation. So VDSQ equals to half of VDD. This VDSQ equals to half of this total is VDD and this is half of the VDD. This is the midway. And IDSQ equals to this voltage, this amount of voltage by source resistance plus load resistance. So half of VDD by RS plus RL. So this point is IDQ and this point is VDSQ. So moving to our next slide. There is one important parameter equation, that is shockless equation. So shockless equation is actually coming from the point that the saturation region actually. It is also known as saturation region or amplifier region equation. Here the JFET operates as a constant current device because ID is relatively independent of VDS. It is due to the fact that as VDS increase, channel resistance also increases proportionally, thereby keeping ID practically constant to IDSS. And it should be noted here that the reverse bias required by the gate channel junction is supplied entirely by VDS here as VGS 0 in this case. So the drain current in this region is given by the shockless equation. That is when the saturation current is flowing through the device or through the JFET. So what is Shockley's equation? Shockley's equation is IDS equals to IDSS in bracket 1 minus VGS by VP whole square. So in place of VP, we can put here also VGS off. So IDSS in bracket 1 minus VGS by VGS of whole square. So if we go through the drain characteristics of JFET, we can see that this part of the characteristics is linear, indicating the ohmic region, indicating that for the low values of VDS, current varies directly with voltage following Ohm's law. It means that JFET behaves like an ordinary resistor. Till point knee voltage is reached, and then the nonlinear region, actually it is the region ID increases at inverse square law rate up to point B, which is called pinch-off region. As we know, what is pinch-off region? This point is actually does not signify the current is off, rather current is maximum at this point. And after that pinch-off region, we find that the saturation region, here Shockley's equation is applicable. So this equation can be rewritten as VGS equals to VGS of in bracket 1 minus root over of ID by IDSS. Similarly, if we express it in the form of transconductance, then transconductance in the form of, we can write that GM equals to minus of 2 IDSS by VP in bracket 1 minus VGS by VP, or GM equals to GMO 1 minus VGS by VP, and mu equals to RD GM. Now let us explain what is mu, what is RD, what is GM elaborately. So moving to our next slide. This is the numerical problem. Let us first explore this numerical problem. Calculate the amount of gate to source voltage necessary to regulate a JFET drain current at a value of 2.5 milliampere. Given the following transistor parameter, VGS is 3 volt, IDS is 17 milliampere. So I know the formula now, or you know the formula now. Just put the values, you will get VGS equals to 1.85 volt, because now IDSS you know 17, VGS 3 volt you know, ID is given 2.5 milliampere. 3 unknowns are known now, and you will find VGS equals to 1.85 volt. This is problem 2. From the double check measurements taken with these 2 meters, identify the terminal of this JFET and also what type of JFET it is. So this is actually gate, left one gate, and other 2 terminals are source and drain. Now black one is ground terminal, black of the multimeter is ground terminal, and red is the positive terminal. So this ground terminal is connected to gate, and this positive terminal is connected to source or drain. Similarly, these 2 terminal, either source or drain terminal, these 2 terminal of the multimeter is connected to source and drain. Here we can see that resistance is coming 0.015. And here we can see the resistance is coming 0.743. So resistance is much more in this case. That means this junction obviously reverse biased by the battery of this transistor as the battery of this multimeter, because the multimeter is connected across these two terminals. That means multimeter battery is connected across these two terminals. So this positive should be connected to negative, otherwise it won't be reverse bias. So gate negative means gate is N, and gate, if gate is of N type, then the channel should be is of P type. So this is a P channel JFET. And here the resistance is showing much less, as both are P type, P channel source and drain are connected to same terminal, because source and drain actually the bulk. The minor resistance variation that we are getting due to the variation in the depletion layer width. So this reading suggests that the FET is of P type. Moving to our next slide, this is problem 3. Determine the value of RS required to self-bias a P-channel JFET with IDSS equals to 25 milliampere, VGS off equals to 15 volt, VGS is to be 5 volt. So ID equals to IDSS 1 minus VGS by VGS of whole square. We know the Shockley's equation. Put all this formula, we are getting ID equals to 11.1 milliampere. Now we have to determine the source resistance, RS. So RS equals to VGS by ID, that is 5 volt by 11.1 milliampere, that is 450 ohm. Now here is one more example, problem 4. That is, determine the value of RS required to self-bias an N-channel JFET that has the transfer characteristic curve shown below. So this is very interesting problem. From the graph, ID we are getting 6.25 milliampere, which is showing here ID, and VGS equals to minus 5 volt. So RS equals to VGS by ID. So put 5 volt by 6.25 milliampere, that means 800 ohm. So this is very simple but interesting problem. This is problem 5. Determine the drain resistance for VGS equals to 0, minus 1 volt and minus 4 volt. So IDSS, say from data sheet, we may get that IDSS equals to 9 milliampere. If the particular FET is given to you. So from data sheet, we can collect the data that IDSS equals to 9 milliampere and VGS off equals to minus 8 volt maximum. From data sheet, all these we are getting. Now VGS equals to 0. So ID equals to IDSS equals to 9 milliampere. Right? We know that when VGS equals to 0, ID equals to IDSS. That means ID equals to 9 milliampere. But when VGS equals to minus 1, now we have to have the Shockley's equation. We know ID equals to IDSS 1 minus VGS by VP whole square. So put all the values, because VGS off is known, minus 8 volt. Now it is there. And VGS is minus 1 volt. Just to find out the ID, that is 6.89 milliampere. Similarly, for VGS equals to minus 4 volt, ID is becoming 2.25 milliampere. So moving to our next slide, here is one more example. Determine the value of RS required to self-bias a P-channel JFET with IDSS equals to 25 milliampere and VGS off equals to 15 volt. So we know the Shockley's equation. Now put all the values, it is becoming 11.1 milliampere. And now determine the value of RS, VGS by ID, that is 5 volt by 11.1 milliampere, that is 450 ohm. Now there is one more problem. The reverse gate voltage JFET when changes from 4.4 volt to 4.2 volt, the drain current changes from 2.2 milliampere to 2.6 milliampere. Find out the value of transconductance of the transistor. So the transconductance GM is defined as del ID by del VGS, where ID is the change in drain current when change in gate to source voltage is VGS. So del ID is given 2.6 minus 2.2, that is 0.4 milliampere, and del VGS equals to 4.4 minus 4.2, that is 0.2 volt. Therefore, GM equals to 0.4 milliampere by 0.2 volt, that is 2 millimho. Here is one more example. The device parameter for an N-channel JFET are maximum current IDSS equals to 10 milliampere, pinch of voltage VP equals to minus 4 volt. Calculate the drain current for VGS equals to 0, minus 1 and minus 4 volt. Similar type of example. So IDSS here, ID equals to IDSS 1 minus VGS by VP whole square. So when VGS 0, we know ID equals to IDSS, that means 10 milliampere. But when VGS equals to minus 1 volt, follow the Shockley's equation, put all the values there, and you will find ID equals to 5.6 milliampere. Similarly, when VGS equals to minus 4 volt, you will be getting ID equals to 0. That is, it is coming from the Shockley's equation. So there are few review questions. Draw the structure of JFET and discuss its working. This type of questions are very fruitful for the BTech students. Let us have a look. So moving to our next slide. This is the reading material. If there is any question, feel free to ask me to this email ID. There are so many review questions present in this slide. If you find any problem in solving this, please mail at this email ID. Thank you.